Good morning, HASP scholars. It is Thursday, February 8th, and we're excited to have you joining us this morning for Climate Change Tipping Points, presented by David Karowe. I have Bill Wells, our coordinator here, who will get started here very shortly with our introductions. And I apologize, the sun is in my face on what is going to be a 55-degree day here in Holland in February, so I think this is the appropriate subject for today's conversation. But we're happy to have David Karowe joining us. As a reminder, if you'd like to submit questions for him during the presentation, you can share those in the chat window at the bottom of your screen. You should have already seen a welcome there from Gloria Goodwin, our course technician. You can just write right in there, and Gloria will keep track of those questions, and we'll answer those at the end of today's session. Also, just want to remind you that next Tuesday, February 13th, is our February monthly program. We're happy to welcome Dave Koster of Holland BPW to talk to us about new projects and new energy goals coming out of the City of Holland. So with that, I'm going to pass things off to Bill Wells, who will introduce our speaker today, and hope you enjoyed today's presentation. Thank you.
Good morning, HASP members, and welcome to Climate Change Tipping Points. What are they and why should we care? Our presenter today is David Karowe from Western Michigan University Biology Department. I'll read it so I don't mess up his bio here. David Karowe is Professor of Biological Sciences at Western Michigan University. He received a BS from Harvard University and a PhD in ecology and evolutionary biology from the University of Michigan. Karowe's research interests include global change ecology, and he has received numerous federal grants in support of climate change research and training. So I guess Ian pretty much outlined how we'll handle questions today. So I'm just going to turn it over to David. Welcome, David.
Thank you, Bill. And thank you for the introduction. Can you hear me okay?
Yeah, you're a little quiet, but I can hear you.
Okay. If anybody can't hear me, could you please just write something in the chat? And I guess Ian will let me know, and I'll try to get closer to the mic. Okay, so today's topic is something that was not really even on the radar for climate scientists until about 15 years ago. These phenomena are called tipping points, and tipping points are probably numerous in our climate system, and they are temperatures at which something changes very fast on our planet. The thing that changes very fast is called a tipping element, and the point at which it changes is called a tipping point. There are large changes past the tipping point very rapidly. They don't always involve temperature. So the tipping points that we'll talk about have consequences for global temperature, but their major consequences are other things, like sea level rise. Okay, so before we start, Bill's seen this video a lot, but it's one that I think everybody should see. This is a 30-second video, a 30-second record of temperature change on our planet. And the colors on any place on the map tell us whether during the 5-year period listed at the top, that place was warmer, cooler, or the same temperature as the same place was during 1950 to 1980. Okay, so for instance, in this first five-year span, most of the planet was cooler than it was in 1950 to 1980. And what we'll do is just see if temperatures change as we go up to 2022, I believe. Okay, so there's no question that temperature has been changing. That's the global warming part of climate change. And one thing before we go to the next slide, I'd like to point out is that clearly you can see that the warming has been greatest in the Arctic and in parts of Antarctica, especially the West Antarctic ice sheet in the Antarctic and the West Antarctic Peninsula. And not surprisingly, those are the places where we expect these tipping points will be reached soonest. And in fact, this is a qualitatively different kind of warming than any in the ice core records, which go back at least 800,000 years. It's way faster. So, and it's also happening while the sun is solar energy reaching the Earth is actually decreasing. And increasing solar energy is what caused all past warming episodes over the last 2 million years. So it's quite clear that it's human caused. Oops. Okay, so we'll talk about different possible levels of global warming, different possible futures. And right now we have a choice of a lot of different futures. We can still alter our emissions behaviors to make the better futures, one of the better futures come to be, but we have to do that quickly, and especially before we start to pass some of these tipping points. I want to put three possible futures in the context of the past 400,000 years. What we're looking at here is carbon dioxide level in the atmosphere. And it went up and down with the temperature cycles, roughly 100,000 year cycles. But over the last 400,000, actually last 800,000 years, it never got to 300 parts per million. It always was between 180 and 300 parts per million. We passed 300 parts per million a little before 1950. We're actually up at about 420 right now. And three possible futures are usually referred to as business as usual, which is basically that we keep doing what we're doing, which includes shifting very gradually to clean energy sources, but at the same time increasing total global energy use. If we continue along our current path, then carbon dioxide levels in the atmosphere reach 950 and Earth warms about 5 degrees Celsius relative to what it was before the Industrial Revolution. Paris Agreement, which I would think you've all heard of, maybe know quite a bit about, says, no, we're going to reduce emissions enough to have atmospheric levels stabilize at 550 parts per million. We're right now about 420, and that would limit warming to somewhere around 2 degrees. The Paris Agreement also said we're going to try to do better than that. What I call Paris Extended is a future where we maybe overshoot, but eventually stabilize atmospheric CO2 at 450 parts per million, and that would result in about 1.5 degrees global temperature rise above pre-industrial. A lot of the tipping points we'll talk about, we think will kick in between these two. Maybe even by 1.5, but certainly by 2 degrees. So the future we're headed towards will probably have all of these tipping points. So one of the questions that the discussion of tipping points raised is, okay, temperature is predicted to change relatively smoothly, but does that mean that all the things that temperature affects will also change relatively smoothly? And I'm just going to modify this figure. We'll see this again in the talk. So it provides the change relative to two baselines. One is 1995 to 2004 average. One is basically pre-industrial temperatures. We're not interested in comparing to recent temperatures, where all of the tipping points are expressed relative to pre-industrial temperatures. So we'll get rid of that axis, and we'll look at the three, or we'll keep in mind the three emission scenarios and possible futures that we just talked about. So I'll get rid of some of them that aren't going to come up again. Business as usual gets us to actually probably more than 5 degrees, but we'll call it 5. Paris Agreement gets us to 2 degrees warming by end of century, and Paris extended 1.5, although it may overshoot 1.5 and come back down. Okay, so we'll see this again. And in the context of individual tipping points. So Earth has a lot of what are called tipping elements. Each tipping element has its tipping point. Tipping element is a big part of Earth's climate system that is capable of, vulnerable to large and rapid changes with a very small change in temperature, but that small change has to occur at the tipping point, has to cross the tipping point. So a tipping element in this figure would be the mountain, and the tipping point, which is the critical temperature at which that small change does actually qualitatively change the state of the tipping point, that would be the peak. So pushing the globe makes small changes in its position till you get to the peak, and a little bit more pushing causes it to roll down the other side. So that would be a tipping element and its tipping point. We don't really know how many tipping points there are. It's relatively new part of climate science, and different authors, different study groups, research groups identify different tipping points. There's a general consensus that these 9 are not only tipping points, but what are called core, global core tipping points, which means that when they tip, they will have a global effect. It won't just be regional. And they are all large parts of the climate system. We'll talk about 7 of them. Okay, so remember, past the tipping point, things change very quickly, and it's usually because there's one or more positive feedbacks that make large future changes inevitable and very likely permanent, irreversible. So let's talk about the Greenland ice sheet as a tipping element. And just to remind you what we saw at the end of the video, that the Arctic and parts of the Antarctic have been warming much faster than the rest of the planet. It's somewhere between 2 and 4 times as fast as the planet as a whole. This is from the relative warming from 1975 to now, basically. So Greenland is in the zone of our planet that's gotten that's experienced global warming quite strongly, and as a result, of course, its ice sheet is melting now. Ian, can you, let me see.
If you hit escape, David, you should be good.
Okay, just escape. Okay.
Yep.
And share some?
No, we can, no. Okay, why don't you go back to share again? That's okay. There we go. You can see your screen now. Yep.
You can see it? Okay. So here is a video showing melting of the Greenland ice sheet and consequent changes in ice mass. The annual cycle, of course, involves growing a little bit during the winter and then melting more than that growth in the summer. And one thing that's interesting in this video, at least to me, is that it shows also the direction of movement on the Greenland ice sheet. This is important because the tipping element involves clearly accelerating the movement of those parts of the ice sheet. So here's what has been happening. And I hope you can see that there is motion. Every one of those orange areas has motion of ice moving from the center of the ice sheet towards the ocean. And there are certain parts that are losing mass a lot. And those are really the glaciers that are flowing into the ocean. Notice that the center part of Greenland ice sheet is actually growing a little bit. Okay, so the Greenland ice sheet is melting. Its glaciers are slipping into the ocean relatively quickly. So the question is, why is this a tipping element? That doesn't say it's a tipping element. It has to somehow have a high probability of responding non-linearly to future warming. And the thinking is it will respond non-linearly because there are a number of positive feedbacks that are built into the Greenland ice sheet. One is called the melt elevation positive feedback. Here's essentially a topographical map of the Greenland ice sheet.
David, I apologize for interrupting you, but we're still looking at your YouTube screen. So if you could revise your share and go back to your PowerPoint.
That? Can you see the PowerPoint now?
You're not sharing anything right now, but if you would try to share one more time.
Okay. I should know this.
No worries. There we go. We can see your screen now. If you just want to make that full screen, we can be able to read it better.
Okay, so I asked, why is
Thank you.
the Greenland ice sheet a tipping point? And it's because it does have positive feedback loops that are inherent in the ice sheet. This is a topographical map of the Greenland ice sheet where you can clearly see it's a lot taller. It's a lot higher in the center. And this melt elevation positive feedback occurs when melting reduces the height of the ice sheet. And that means that the ice now is in contact with air at lower altitude, which is going to be warmer. So it exposes the ice sheet surface to warmer air temperatures as it melts, as the elevation decreases, and then that accelerates melting. Okay? So that's one positive feedback. Another is called the melt albedo positive feedback. Albedo means reflectivity. A high albedo surface bounces most of the sunlight right back out to space. A low albedo surface absorbs the sunlight and as a consequence heats up. So snow is has quite a high albedo. But when it melts, it exposes less reflective, lower albedo ice underneath. There's snow on top, but there's ice underneath. And the ice actually is less reflective. So now the surface of the Greenland ice sheet absorbs more sunlight, converts it into heat, and that accelerates melting. Don't worry about the unit. This is change in albedo over the last decade or so, where or change in heat absorption as a consequence of albedo change. The warm colors are areas of the ice sheet that are now converting more sunlight into heat. They're less reflective. Only one small part has become more reflective. And those colors represent places on the Greenland ice sheet where the positive albedo feedback, melt albedo feedback is happening. And it's not only that ice is exposed, it's also that the melting snow and melting ice sometimes pool on the surface, creating meltwater lakes, and those absorb even more sunlight than the ice surface itself. There's also a positive feedback that's called the melt runoff feedback. Here's part of the surface. This would be in the summer when there's a lot of melting going on. You can see the meltwater, I hope, going down into this hole. A lot of the surface meltwater will go through crevasses or whatever and actually reach the bedrock. So as meltwater flows through those crevices to the bedrock, it actually, once it gets to the bedrock, it actually acts as a lubricant. And that makes the glaciers flow faster into the ocean. So again, a positive feedback. And now we can ask, okay, it makes sense that Greenland might have some tipping points, or at least a tipping point, at which the loss of ice accelerates and essentially becomes irreversible. And the best estimate now, this is pretty strong consensus, is that occurs at about 1.5 degrees Celsius above pre-industrial. If that's true, if that's accurate, we're really close to that tipping point. We've already warmed about 1.1 degrees. When are we likely to pass the Greenland ice sheet tipping point? When we reach 1.5 degrees, that's that dotted line. And doesn't really matter which emission scenario we follow from here on out. They all pass that, make us pass that tipping point around, well, mid-century, maybe a little bit later. And it's possible, if it's less than 1.5 degrees, it's possible that we've already passed the tipping point. Now, when a tipping element passes the tipping point, it doesn't mean that the change occurs immediately. The change will, in many cases, need tens or hundreds or occasionally even thousands of years to fully occur. What we can ask them, what would be the consequence of it exceeding this tipping point, which it really does look like, if we haven't already, we will soon exceed it. A big consequence of many of the ice sheet tipping points is very large rise in sea level. Wouldn't happen immediately, but it would be probably 3 meters sea level rise within 300 years and 7 meters if the entire ice sheet melts, which would take probably about 10,000 years. Here's what a 3-meter sea level rise would do to our Gulf and Atlantic coast. All of the blue area is now underwater. And it includes not only New Orleans, which is the most vulnerable city. New Orleans basically is all underwater with a 3-meter sea level rise. But so are many, so Miami, of course, but so are cities that you might not think as vulnerable to sea level rise. Washington, Philadelphia, New York, and Boston, for instance. Here's what New York presumably would look like if it experienced, if there was a global 3-meter rise in sea level. Okay, second tipping point we'll talk about is in the permafrost up in the boreal region. So the permafrost is the tipping element, and we'll talk about why it is likely to have a tipping point, why its change will probably be nonlinear. Okay, permafrost is any soil, sediment, even rocks, but organic matter, any kind of organic matter that's been frozen constantly for at least a few years. In the permafrost, in the tundra, the permafrost is the top. Well, actually, the permafrost can go down several hundred meters. The very top of it, usually about the top 1 to 2 feet, is called the active layer. That's the layer that warms up in the summer enough that it's no longer frozen. But more material will accumulate on top of this year's active layer, and eventually it'll be buried below enough material that it won't thaw in the summer. So we have the active layer. That's where decomposition happens and so on for a short time during the Arctic summer. And then all of the rest of this is also permafrost. Decomposition happens only in the active layer, so the carbon that's deeper than the active layer is not getting back to the atmosphere. And most of that carbon in the deeper layers has been there at least 10,000 years, some of it much longer than that. But warming makes that active layer deeper. It increases decomposition, and that results in release of conversion of permafrost carbon into either carbon dioxide or methane, and gets released to the atmosphere. So this is clearly a carbon positive feedback. Let's see. I think I will not show this video. It's not a spectacular video in any case, but it does show that the southern edges of the permafrost, pretty much wherever they are, have been melting fairly rapidly. And we can see that also on this figure. So there's a carbon positive feedback. That's what allows the permafrost to be a tipping point, or to be a tipping element. Warming makes the active layer deeper, and then that releases methane and carbon dioxide, which accelerates warming. Here is in the recent decade, the average ground temperature during the summer, during the northern summer. Any area with those colors is above freezing during the summer. And the darker the color, the farther above freezing it is. Those are places where the active layer of the permafrost is getting deeper and where the carbon is being released. So those are areas where permafrost is already thawing. And it's not a trivial amount of carbon that's in there. The permafrost soils in the northern hemisphere, there's also a little bit of permafrost in Antarctica and some in the Himalayan plateau. The total carbon there is about twice what's already in the atmosphere. So if it all gets released into the atmosphere, it would cause a rapid acceleration of warming. But it isn't going to be all released very quickly. It'll take a long time. It's also the case that melting of the permafrost causes it to be unstable, and you get these little landslides or whatever. The disturbed soil as a result of permafrost thawing is called thermokarst. Okay, so the flat tundra with a 2-foot deep active layer, not thermokarst, but a lot of the tundra has become quite unstable, and you get slides that expose large parts of this deep carbon, this deeper permafrost, to warmer temperatures. And not surprisingly, then, carbon release from these thermokarst formations is a lot faster than from intact permafrost, like we saw in the previous slide. Sometimes those unstable points end up being filled with water. The topography that they make ends up becoming a thermokarst lake. If so, then for the most part, methane is emitted from these lakes. Here's a thermokarst lake. That's a bubble of methane trapped now in the ice, but be released when that ice melts in the summer. And the reason is that oxygen can't get to the substrate underneath these lakes. And so if there's no oxygen, the decomposers can't make CO2, but they can still make CH4. And so methane is released instead. And methane is, molecule per molecule, a much stronger greenhouse gas than carbon dioxide. It's about 80 times as strong over the first 20 years. So that's a serious concern. It's not surprising that thawing not only will be much greater by end of century, but that it depends on our emissions choices. So what I would ask you to look at is the amount of area that's red in this map. That's area that basically has little or no permafrost. So right now, it's the southern and southwestern part of Alaska. Under business as usual, by 2100, the permafrost is basically gone. From actually, it's reduced. The area that has permafrost that is not red, it's reduced by 75%. By end of century under business as usual. Under Paris Agreement, it's reduced, not quite as much, it's reduced, let's say 50%. So, but in either case, we have the return of a lot of carbon to the atmosphere. Most of the carbon is deep enough that it'll take centuries or millennia for it to return to the atmosphere unless it's in a thermokarst formation. So what are the tipping points for this boreal permafrost? For local, abrupt thawing via thermokarst formation, that is predicted to accelerate dramatically above about 1.5 degrees, which again is very soon. If it's low, tipping point is lower, we've already passed it. So again, if so, we're very close and may already have passed it. For collapse of the non-thermokarst tundra globally, the expectation is that tipping point will happen about 4 degrees Celsius. Now, if you remember the path we're on, emissions path we're on gets us to 5 degrees Celsius by end of century. But Paris Agreement and Paris Extended do not. In fact, they never reach 4 degrees above pre-industrial. It's really only the business as usual, of the ones we're discussing, only the business as usual scenario. So permafrost thawing can also cause other problems. They're not necessarily positive feedbacks, but they certainly are consequences. About 50% of the infrastructure that's currently sitting on permafrost is predicted to be at risk. So roads buckle, buildings crack. And the estimate is that permafrost thawing will affect 120,000 buildings, 25,000 miles of roads, and about 6,000 miles of pipelines, which of course has its own consequences. It's interesting to read the arguments of the major oil companies that we need to open up the Alaska National Wildlife Refuge to oil drilling because soon it will be too unstable to put the equipment there and the infrastructure. Okay, one thing that's received a lot of attention, we don't really know if this is going to happen, but it's possible that melting permafrost also causes the release of long buried, long frozen pathogens from the soil. And among those that may be released are anthrax, smallpox, and then plant pathogens as well. These have been found in permafrost that maybe has been frozen for 50,000 years. Whether they would lead to outbreaks, disease outbreaks, we don't know. Okay, so another one that's also mostly a northern hemisphere, almost Arctic tipping element is called the Atlantic Meridional Overturning Circulation, abbreviated AMOC. That's there, and it's also known as thermal haline circulation, THC, and sometimes the Great Ocean Conveyor Belt. If you've heard those terms, that's what we're going to talk about now. The Great Ocean Conveyor Belt is a massive current in the ocean that moves from off the coast of Greenland down to off the coast of Antarctica. In this image, where the current is in red, it's at the surface. Where it's blue, it's deep. You can think of it as a bottom current. And of course, that means it has to go from the surface to depth, and it has to come back up in order to continue operating as a circuit. And what is of concern is what's happening up here where the current descends. Okay, so warm surface water, including the Gulf Stream, is part of this, moves a lot of heat north. And so the North Atlantic is a lot warmer than it would be without the Gulf Stream and this current in general. So that's the movement, that's the current moving heat up into the north. But when it gets up into the North Atlantic, of course it's warmer than the other water around it. So it evaporates, more water evaporates from the current. And also as it freezes, the salt doesn't leave in the ice. The salt remains in the water, so it becomes more saline. And both of those things make the water more dense, and that's what causes it to sink up here. So that's where we get the bottom current, and then the current, of course, has to return to the surface. It does that off the coast of Antarctica, and it brings nutrients to the surface when it comes back up. It's an upwelling current, which is a huge reason why the ocean, the Southern Ocean around Antarctica, is so productive. It's an enormous current. At any point in the current, about 18 million cubic meters pass by per second, and it takes about 1,000 years to make the whole circuit. Okay. What could cause this to tip to a different state? Things that happen that affect its ability to increase density and therefore sink. That's what can cause it to be a tipping point, or that's what can cause a tipping point to be crossed. So what would cause this current to slow or shut down? One big thing is, remember, Greenland's melting like crazy. That's a whole bunch of fresh water entering the North Atlantic, pretty much right where that current sinks. And fresh water is less dense than salt water. So it would essentially dilute the salt water, make it less dense, and potentially prevent it from sinking. There's also been, and predicted to continue to be, increasing precipitation over the North Atlantic, over northern latitudes in general. And of course, rainwater is fresh water, which would dilute and therefore make less dense the current, the water in the current. It's clear that that would have major consequences for the distribution of heat on our planet, and also distribution of carbon. So if the AMOC were to slow down rapidly or even stop, there would be very different patterns of heat and carbon on our planet. Remember that the warm surface water carries heat to the North Atlantic. Hold on. I seem to have doubled this slide. Yep, sorry guys. Okay, so we'll get back to that. What's the tipping point for collapse of the Great Ocean Conveyor Belt? Long term, it's probably about 4 degrees C. That is a tipping point that would not be reached under any of the emission scenarios except something close to business as usual. And if we adhere to the Paris or Paris extended commitments, this great ocean conveyor belt will not tip to either radically slowed or stopping. What would be the consequences of actually passing this tipping point? So one would be, as you'd suspect, since it's bringing heat up into the North Atlantic, if it's not doing that anymore, then there's very rapid cooling of the North Atlantic predicted, possibly by, well, certainly by at least 3 degrees Celsius, possibly by 20 degrees Celsius within a century, probably within 3 decades. There would be corresponding warming of the southern hemisphere, but nowhere near as dramatic as the cooling of the North Atlantic. It's a smaller space here, and the heat now that isn't getting brought to the North Atlantic is now remaining or being distributed over a larger area in the southern hemisphere. So the southern hemisphere doesn't warm as much as the North Atlantic cools. But that, if you've ever seen a movie called, I think it's called The Day After Tomorrow, it actually is a sort of a sci-fi movie based on this phenomenon, where all of a sudden the North Atlantic becomes very, very cold. Northern parts of the U.S. freeze. All of a sudden have an ice sheet, and the United States has to ask Mexico if we can immigrate to their country. Kind of an interesting scenario. It also would remove a huge carbon sink. Okay, when that water, when it's coming as a surface current across the equator and so on, it's picking up a lot of carbon dioxide from the atmosphere. When it subducts and becomes a deep current, a lot of that carbon dioxide gets deposited as carbonate. So it absorbs carbon dioxide while it's at the surface, it transports it to the deep ocean when it sinks, and that's basically carbon that's not going to get back to the atmosphere for millennia. But if the current doesn't operate well, then that carbon stays in the atmosphere. The AMOC accounts for about 30% of carbon dioxide uptake in the North Atlantic and corresponding land areas. So it would be consequential to have that not happen anymore. Okay, let's shift to the other pole and talk about Antarctica. Antarctica is where most of the ice on our planet is. It's way more than in Greenland. And there are parts of the Antarctic ice sheet that are more unstable, more likely to tip than others. The West Antarctic ice sheet, which is here, and it usually includes also the West Antarctic Peninsula, is distinct from the East Antarctic ice sheet. East Antarctic ice sheet is enormous and is melting, but it will melt slowly. The West Antarctic ice sheet is melting a lot faster, and glaciers like the Thwaites glaciers are speeding up in how fast they get to the ocean. Okay, so what is it that prevents that ice sheet from totally slipping into the ocean? It's basically the ice shelves. So ice shelves are protrusions, extensions of the ice sheet over the water that are still attached to the ice on land, but they're floating. And they actually act as a buttress, sort of as a plug that keeps most of the West Antarctic ice sheet from slipping into the Amundsen Sea. Here are some of the ice shelves on the West Antarctic ice sheet, and it's an enormous amount of ice. But the key point is that there's water under here. It's not land, and we have our ice shelf here. the glacier is flowing, but this ice shelf, because it is where it's not floating, it actually is sitting on top of the bedrock. That grounding makes the ice shelf relatively resistant to getting pushed by the glacier. So it acts as a brake on the glacier's movement to the ocean. But the ocean right off of West Antarctica, the Amundsen Sea, is warming faster than most places in or around Antarctica. So here we have that sea, and that is causing the ice shelves to shrink for one and shatter. If they get thinner, they can shatter. And so the brakes on the West Antarctic ice sheet are becoming less and less strong. So it's causing the ice shelves to melt faster, and that makes it harder for them to hold back the rest of the ice sheet. What's the tipping point? Probably about 1.5 degrees. You know, where all of a sudden the buttresses are gone and the West Antarctic ice sheet moves much faster into the ocean. And again, if it is there, if that's the true tipping point, then we're either very close or may already have passed it. What's the major consequence of passing this tipping point? Sea level rise. You notice we haven't really talked about consequences being temperature consequences. And for major tipping points, it's not. And certainly for tipping points that involve ice, the typical major consequence is sea level rise. West Antarctic ice sheet collapse, it would play out over centuries, but it could cause an additional 1/3 of a meter rise by 2100, which is about 30% more than is predicted under business as usual. By 2300, 2 centuries later, 1.5 meters, and in 1,000 years, about 9 meters. That's all of the West Antarctic ice sheet. And you saw what 3 meters would do to New York City. 9 meters would, of course, be disastrous. And it would increase global temperatures a little bit, about 1 degree Celsius by 2100, because there is an albedo positive feedback. If the ice sheet moves into the ocean, then, and if the ice sheet melts, then more dark ocean water or possibly even dark land is exposed, which has a lower albedo and therefore warms faster. East Antarctic ice sheet is fortunately something that isn't likely to tip for a long time. Okay, East Antarctic ice sheet, here's our West Antarctic ice sheet, and East Antarctic ice sheet is virtually all of this gray area. And so what I'll do now, if we can do this, is show changes in all of the ice, on predicted changes in Antarctica as a function of global mean temperature change, so global warming. Across the bottom is temperature. You'll see this ball diverge, and the top line that decreases fairly smoothly is total ice mass. The bottom line is change in ice mass, basically. So see what's predicted. We're about here right now. So we've seen some at 2 degrees, 1.5 or 2 degrees, we see a big disappearance of West Antarctic ice sheet. And then things are predicted not to change a whole lot till we reach the tipping point for the West Antarctic ice sheet, which ideally we never will reach. But it would be at about 7.5 degrees, and you can see here we have a second period, short period of very rapid ice loss. So 2 tipping points in Antarctica, a closer one for the West Antarctic ice sheet, a more distant one for the East Antarctic ice sheet. Full melt of the East Antarctic ice sheet would raise sea level by almost 60 meters. I mean, the vast majority of coastal cities would be uninhabitable. But that's going to take probably, even if we continue along business as usual, probably about 10,000 years. Okay, I'm going to talk a little bit about the Arctic sea ice. These will be the last ones we talk about. It turns out that summer sea ice, which is probably the biggest effect, the most widely understood or known effect of warming on ice, is disappearance of the summer sea ice. That's actually not considered a tipping point because it doesn't have any threshold behavior. The Arctic winter sea ice is considered a tipping point. Okay, the Arctic Ocean, the Arctic sea ice typically reaches its maximum extent, its maximum area in February, late February, early March. Here's March of last year. And, you know, pretty much, not pretty much, the whole ocean, Arctic Ocean is covered by ice. What has been happening, the area of this ice has been decreasing slightly in the March ice area. But the real change is one that satellites can't see. And that's that the warming of the ocean, especially the Arctic Ocean, has made that ice thinner. Okay, it has less time to form, and the water underneath it is warmer. So it's actually become only about half as thick as it was in 1980. The sea ice in March has decreased by, the area has decreased by about 2.5% per decade. I mean, it's clearly happening, but it's not approaching a tipping point. Well, sorry, it's not. That's not what's going to make it hit its tipping point. Okay, so we already saw that warming winters and warmer ocean temperatures of the Arctic Ocean have caused this very large scale thinning. Okay, I'm going to have to proof this PowerPoint before I give it again. This is the first time. I just put this together this last week. Okay, so in terms of thinning, you can ask, well, how much thinner was the Arctic sea ice in March of 2023 compared to the average over the last 20 years? Areas that are in red here were substantially thinner than normal, than has been normal for the past. And there are a few areas that were thicker, but overall the thickness is decreasing by 47%. And the reason that this can create a tipping point is that thin ice is a lot more vulnerable to rapid complete melting than thick ice is. And if you've ever watched ice out on a lake in Michigan, what you see is that as spring comes along, there's a bit of melting around the edges, and that increases slowly, and then in a day or 2 days, all the ice is gone. What's been happening is it's thinning that whole time, and now it's very easy to get rid of a whole bunch of area of very thin ice. And the worry is that's what's going to happen to winter sea ice in the Arctic. Probably not for a long time. The tipping point for that collapse, basically rapid disappearance of winter Arctic sea ice, is probably about 6.5 degrees. And it would, because of the albedo feedback, cause an additional maybe 0.5 to 0.6 of a degree rise. It would not change sea level because it's already floating. It's like when ice cube melts in your glass, it doesn't make your the liquid level higher. Okay, so that wouldn't affect sea level, but it would have a feedback effect on global temperature. Talk a little bit about kind of the elephant in the room that turns out to be a mouse in the room, because it's not a tipping element. That's the minimum extent. It's summer sea ice. Usually the summer sea ice or the Arctic sea ice reaches its minimum late August, early September. Okay, here is the minimum last year, September 19th of 2023. The color actually indicates thickness of the ice, so the whiter it is, the thicker. But if we just look at the area of September sea ice compared to the median area from a 30-year period, 1981 to 2010, there's clearly a lot less ice than there used to be. Okay, and here is the 2.5% decrease in winter sea ice. Here's the decrease in summer. September sea ice in red, it's about 13% per decade. So summer sea ice has been disappearing about 5 times as fast as winter sea ice. And in fact, this decline that we've seen is something that probably has not happened for at least 1,500 years, but probably hasn't. The last time it got this low was probably about 10,000 years ago, maybe a little bit more. So if we look at the minimum area in September, at the year 600 up to today, what we see is, yeah, it went up and down, but this decline is unprecedented. And it's not considered a tipping point because so far, and presumably in the future, it responds linearly to global increase in temperature. Here's the record minimum September sea ice. This is 2012. But it didn't cause a rapid decline in summer sea ice after that. You can see here's 2012, and it's not like it accelerated a loss. The summer sea ice has actually rebounded a bit since then. So it has a strong feedback, positive albedo feedback, but it doesn't look like there's any threshold for collapse. So it's not considered a tipping element. It's considered a threshold-free feedback. I mean, it keeps happening at about the same rate. There's no prediction that the rate of decrease will suddenly become much greater. On the other hand, it certainly has consequences if we have ice-free summers, not just on the temperature feedback. It's predicted that above 1.5 degrees warming will occasionally have ice-free summers. Above 2 degrees, it'll be common, and above 3 degrees, it'll be every summer. Okay? One of the things that we don't have time to talk about is the biological consequences of these tipping points. Every one of them has massive biological consequences. Think of a coral reef that has to deal with 10 meters of ocean water above it, an additional 10 meters. Okay. The major consequence of loss of summer sea ice is an acceleration of Arctic warming by about 8%. That's the albedo positive feedback. Okay, so we've talked about these 7 tipping elements. There are others that I wish we had time to talk about, and that most of them are regional tipping elements. They don't have global impact, but they include the biosphere. They include ecosystems or things that are essential to ecosystems and humans, like water resources. So for instance, the Amazon rainforest is considered a tipping element. There is a amount of global warming somewhere between 2 and 4 degrees where large parts of the Amazon rainforest become savannas. But there are other regional impact tipping points that I think would be interesting to talk about. One is not just the carbon part of the boreal permafrost, but what happens to the creatures who live there. The boreal forest is likely to have major changes that occur fairly quickly at somewhere around 4 degrees. Coral reefs, of course, are incredibly vulnerable. The changing rain patterns in the Sahara and a potential greening of the desert is likely to have a tipping point. And the glaciers that are not on Greenland or Antarctica, but are extrapolar, that is out of the poles, and they're in mountains. Mountain glaciers melting is, I think it creates tipping. It is, the melting itself has a tipping point, and I think it will create tipping points for human behavior. Okay, so the biosphere does tend to have tipping points, but tipping points that have regional impacts, not global impacts. Although I think the Amazon definitely would, because it's such a carbon sponge, and if it turns into a savanna, it's no longer a massive carbon sponge. Global tipping points, everyone we've talked about, of course, affects the biosphere. It affects living things. We just haven't had time to talk about that. And I would say that we also should think about tipping points in human behavior. And I think there are tipping points that in human behavior that climate change can make us cross, where globally human behavior changes. If there are hundreds of millions of climate refugees due to coastal flooding, that will certainly put stress on pretty much any country that could be a refuge for these refugees. Drought, and this is one in the Sahel, and these are all dead goats. The drought has been so severe, we don't hear about it much, but through many parts of Africa, droughts have been so severe that livestock can't survive. People also have to move. At what point will that create conflict, armed conflict? Actually, it already has. Mountain glaciers, as they shrink and disappear, their provision of fresh water, which over 1 billion people globally depend on, that stops. And so humans can't live in places where they were getting their water from these mountain glaciers. Includes a lot of people in India and China. And I think the tipping point would change human behavior from being somewhat warlike species to being a very warlike. I think it would dramatically increase armed conflict, including potential nuclear conflicts between, for instance, India and Pakistan over the water in the Indus River. So there are tipping points. There are ecological ones. So we've talked about climate tipping points. There are also ecological ones, and I think it's very important to consider that there are human tipping points. Climate change could cause humans to behave as if we're all in our own armed lifeboat, is the way it's often put. I hope that won't happen. Okay, concluding thoughts. Even 1.5 degrees of warming is likely to cause several of these core global tipping points to happen, to become active. And that's particularly true for ones involving ice sheets or large areas of ice. And the main consequence will be sea level rise, but it'll take a while to play out. a bit, actually not a trivial amount by end of century, but massive sea level rise on the timescale of several centuries or millennia. The world has committed in the Paris Agreement to reducing emissions. Each country had its own voluntary commitment, and those commitments would result in probably between 3 and 3.2 degrees of warming. Depends. It depends how many of these tipping points kick in. But that would almost certainly cause additional climate tipping points to be exceeded. So the current commitments are inadequate and unsafe. We have to do better than that. And this growing understanding of climate tipping points, it's really only been a subject of research for 15 years or so. But already it's providing what I think is strong scientific evidence very strongly supporting efforts to limit global warming to 1.5 degrees or less. And possibly to bring it down if it exceeds that. Some of these tipping points are reversible, many are not. But if we could figure out a way to pull carbon dioxide out of the air, we could lower global temperature and we could reverse some of these tipping points, like for instance, Arctic sea ice, both summer and, well, winter Arctic sea ice and also summer, even though that's not a tipping point. So we probably should be doing a lot of research on how to lower, not just cut emissions, but actually reverse global warming. And the safest way and most effective way would be to figure out how to pull carbon dioxide out of normal air. Okay, I think that's it. Thank you very much for your attention. Sorry for the few glitches along the way. But you guys saw the premiere of this talk. So.
Well, thank you, David. We appreciate that. And
Sure.
before we get to questions, I just want to thank you again and thank Bill for your work to bring this course to us. Before we jump into some other questions, I want to invite people, if you have any questions to share with David at all, you're welcome to share those in the chat window. You can find that at the bottom of your screen, type in a question there, and we'll be happy to relay that on your behalf. So David, first question I have for you goes back to something that you opened your presentation with, almost an optimistic tone, saying that there are multiple paths for us to correct some of the behavior that we've done. So I'm curious, what would you say to those on various sides of this conversation that we're beyond help, that there's nothing more we can do and we've crossed all of our tipping points?
We've committed to crossing them. We've committed to emissions that will cause us to cross them in the relatively near future. I would say that's one possible future, but it's not the only possible one. Like I said, I think we can certainly rapid emissions reduction. If we're going to achieve a 1.5 degree future only by emissions reductions, that has to start. We have to start cutting emissions dramatically immediately. Fossil fuel, there's a tremendous amount of money to be made off of fossil fuels. And so there is very strong resistance to any serious emissions reductions. We have the technology that would allow us to run the world on carbon-free electricity. And we could convert most of what we use fossil fuels for to running on carbon-free electricity, like for instance, electric cars and others. And so we could dramatically reduce emissions easily within 10 years if we really wanted to, but we don't. That's obvious. Well, a very small number of people globally really don't want an energy transition because they profit incredibly off of the use of fossil fuels. But I would say, that's CEOs, major shareholders. It's not the gas station attendant. No, it's people who benefit financially tremendously from our continued use of fossil fuels, even and don't care that that comes at the expense of 7.5 billion people. I'd say it's maybe 10,000 people globally who really benefit from it, but they can have a lot of political influence, particularly if campaign finance laws are pretty lax, have a lot of loopholes. Okay, so one of the ways, so I think if someone said it's impossible, we can't get there, I'd say absolutely we can get there. We just, we aren't interested in doing it. I also, the way I look at it, our generation is stealing our children and grandchildren's future. Those of us who are willing to just go along with the way it's always been for convenience more than anything else. What we are saying is we want to live a slightly more convenient life, even though it's going to make your life horrible. And I think that is unconscionable. So I wish more people would want to make this transition happen. But if we, one thing I sometimes say, this is recorded, so I'm hesitant to, but if students say students tell me, I just want to give up, or, it's impossible to make the future livable, I say, well, imagine that we woke up, everybody around the planet woke up tomorrow morning, and there was, everybody could see an alien warship in the sky out there, above their house or their area. And so it was clear that we were now at the mercy of a group that had technology that could just destroy us instantly. And in fact, the message from this alien in blockade or whatever, it was, you've got 10 years to get off fossil fuels entirely, to find different ways to create energy and use it. And we have those ways: solar, wind, geothermal even. And if you don't, if you're still using fossil fuels a decade from now, we will kill all humans. Would the response be, might as well kill us now because we can't do that? Or would it be, okay, we'll shoot for doing it in 5 years just to make sure we have it done by 10? And it undoubtedly would be the latter, which says if we really wanted to, if we were really motivated, yeah, we could make that transition happen. We could hold warming to 1.5 degrees just by cutting emissions. And hey, as long as we're at it, let's figure out ways to remove greenhouse gases, particularly carbon dioxide, from the atmosphere, so that if we overshoot and the tipping point is reversible, we can make it unhappen. So anyway, long answer, Ian. And I don't like to invoke aliens in any explanation, but I think that does put it in context. If we really had to, we could do it. We know we could do it.
Thank you. I now want to hand things over to Gary Morris. Gary, you typed a question into the chat window, but if you'd like to unmute, you're welcome to ask David directly. Otherwise, you can give us a thumbs up and we can read them for you. Gary, why don't you unmute yourself? There, we can hear you talk that way. There we go.
You've been discussing most of what I was wanting to ask about, and that is, do you really think that direct carbon capture from the atmosphere is sufficiently feasible to overcome our miserable political response? Because I think, absent an alien invasion, it's just not possible to get the global economy off fossil fuels fast enough. But is direct carbon capture, in your opinion, feasible?
It's a great question, Gary. I don't know. I mean, we haven't put enough research funding into it. I think it should be top #1 federal, like National Science Foundation, NOAA research priority. But it's not, there hasn't been enough work to know whether it is, well, it's feasible. We can do it. Whether we can do it on a large enough scale to matter, I think we don't know that yet, but probably. Some of the techniques don't involve rare elements or anything that's not in abundant supply. The other obstacle is cost, which is, largely a function of the energy that has to go in to. And if we were generating massive amounts of green electricity, which is the form the energy would be in, by wind, solar, even geothermal, then energy costs would be low. And in any case, I would argue that the cost would be tolerable in any case. But I think the big obstacle here is we just haven't explored the technology, the options to make that happen. So I think it's difficult to know whether it could be applied on a large enough scale to matter. I tend to be optimistic. I think it probably could, but the economic obstacle would disappear if we have abundant, very cheap green electricity. By the way, wind, the turbines that we have now, could produce at least 40 times all of the energy that humans use globally in all forms. So we could make 40 times more energy than we use by our current wind technologies. We could make roughly 100 times all the energy that humans use by any of 3 solar technologies, the photovoltaics, which is what we all see, but then also 2 kinds that involve using mirrors to focus sunlight and create heat. Those are technologies that already could power the transition, that could replace all of the energy we use fossil fuels to generate. We have to change things so that they work on electricity. We have to change transportation and heating and so on. But with better batteries, none of those green electricity sources is intermittent. As long as you can make more than you need during the day or whatever, you have electricity stored that you can use at night. And for the solar ones that involve focusing sunlight and heating something up, you make more heat than you need to generate to meet the electricity demand during the day. So you just store some of the molten salt and make electricity all night long. That's happening in every concentrated solar power plant worldwide that's been built in the last 7 years. So they're already making electricity all night long. So this intermittency issue is basically a deception.
Thank you, David, and thank you for the question, Gary. Next, I want to go to Ron Willis. Ron, if you want to unmute yourself and ask your question directly to David, you're welcome to. Thank you.
Thank you, and thank you for the talk, David. I'm wondering if there's a way to engineer our own tipping point. So rather than the sort of heavy lifting of pulling down carbon, could we make it cloudier in the skies above the Arctic, perhaps, and start our own little feedback loops?
There is some. Okay, so if you're talking around about geoengineering, the general sort of we manipulate the climate.
Yes.
There are two basic strategies. One is bounce more sunlight back to space, basically increase the planetary albedo. And the other is pull carbon out of the air. So the geoengineering that gets the most attention is called solar radiation management. That's the general category. And it's things like put sulfate aerosols into the stratosphere. And they tend to be reflective kinds of aerosols. Several problems with that. I'm not a big fan because we actually could reduce temperature on our planet dramatically within a decade if we did that. It's a very quick solution to temperature problems, but it undoubtedly will affect rainfall patterns, and models aren't yet agreeing on how that'll happen, but it will make some places get much drier, some places get wetter. And that in itself can cause conflict. If we're putting the aerosols into the air, why can't we put them where they will do us the most good, for instance? But another issue is that anything that deals just with temperature and therefore allows continued reliance on fossil fuels costs us the ocean, basically, because carbon dioxide acidifies the ocean when it gets absorbed. And we know that the ocean is acidifying. We know that that is potentially lethal for pretty much anything in the ocean that makes calcium carbonate. So corals make calcium carbonate as the structure of the reef. Of course, all bivalves use calcium, but so do lobsters. So basically, and a lot of the phyto and zooplankton actually make little calcium carbonate coverings. So if we control temperature and that lets us emit more carbon dioxide, then what we're doing basically is trading lower temperatures for loss of ocean. And so that's why I'm not a big fan of it. I'm a huge fan of free air carbon removal, but it's, as we discussed, it's not clear whether it's feasible. I'm sorry, Ron, did I answer your question?
Yeah, you made it. You explained how it's a risky thing with its own unintended consequences. So thank you.
Mm-hmm.
Thank you, Ron.
Oh,
sorry, go ahead, David.
There are other possibilities, like, for instance, fertilizing the ocean. For the most part, phytoplankton, the photosynthesis in the ocean is limited by iron availability. So in principle, we could increase the iron in the ocean, basically dump little iron powder, and increase photosynthesis and draw more carbon out of the air that way. As an ecologist, which is my primary area of interest, we would ask, oh yeah, so what could possibly go wrong with that? And we don't know. I mean, it would definitely cause changes to marine ecosystems that we can't anticipate. And it also may not be that effective. So that's one. Planting trees is always good, but we can't come close to planting enough trees to really draw down carbon dioxide levels in the atmosphere. Yeah, and there are other carbon removal techniques that are less effective and more expensive than the ones we've talked about. So, I don't know.
Thanks, David. We have 2 questions remaining from our members joining us. I'm going to ask if Laura Judge would like to come off mute and ask her question. Laura, if you're still there, you can unmute yourself. Otherwise, we're happy to read it for you. Hi, Laura.
Yeah, hi. Well, 2 questions. One is just kind of ignorant question, but you said something about the summer ice melt doesn't raise the sea levels compared to winter ice melt. And so I kind of didn't understand that. And then also, are you a supporter of the United States enacting a carbon fee to help this whole situation? Thank you.
Great question. So what I meant to say is that any sea ice, any floating ice, when it melts, doesn't change the level of the water. And as an example, if you have ice cubes in your glass and they melt, it's not like you ever have to worry about your glass spilling over. It's not going to change the level of the liquid. So melting of both summer and winter sea ice, as long as it's sea ice, it's not going to affect sea level because it's already floating. It's basically ice cubes in the oceans. And the second question, carbon tax. I mean, we need to do something. And I think the thing that I would support the most is what Citizens Climate Lobby has been suggesting for a long time. It's called a carbon fee and dividend. And the carbon fee and dividend says, okay, we're going to put basically a tax on carbon, and it's going to increase over time. It's going to be low at first to sort of lessen the shock. The fee will increase over time, but it'll be applied at the places where carbon enters the economy, which is refineries, coal mines. It's not gas stations. So the carbon's already well into the economy by the time we see it. That makes it a bit simpler for accounting and so on. About 400 places would be where the tax was applied. The IRS probably would collect it. And then the dividend part is, okay, all of that goes back to American citizens. And it goes back more or less equally. So prices on carbon intensive goods are going to increase. But for the lower 2/3 of earners in our country, the lower 2/3 of households by income, they would get back more each month in their dividend than they would pay in higher prices due to the carbon tax. So it's got a lot of really good components to it. And it would of course be a border adjustment. So other countries' goods aren't cheaper because they aren't taxing their carbon use and so on. So and in fact, fossil oil companies and together with some very prominent past Republican officials have proposed the same thing. The difference in their proposal is there's a little bit of difference in terms of what the tax would be and where it would start and how fast it would go up. But the big difference is it would include immunity for them for any harms they have already caused. And that's what they really want. Yeah, I think. So the kind of progressive climate community says, no, we're not going to give you a get out of jail free card for everything that for the harm you've already caused. And that'll be a sticking point in negotiations for sure.
Thanks, David. And thank you, Laura, for your questions. We have one more, and we have a couple of minutes just to get to this one quick, David. Jim
Sure.
Hagel, if you'd like to come off mute, you can ask your question. Otherwise, we're happy to. Okay, looks like we'll have Gloria. You want to read that for us, please?
Jim's question, is nuclear an acceptable energy source?
Great question. So I'm kind of ambivalent about nuclear, strongly ambivalent. Strongly There's some great things about it. There are some horrible things about it. It all amounts to, in my mind, if I had to choose between coal or coal natural gas as our electricity fuel versus nuclear, I would choose nuclear in a heartbeat. I think the harms caused by burning fossil fuels are so enormous and global. Whereas the potential nuclear accidents were reasonably local impact and and so overall are much less. Nuclear is something that the Palisades plant is probably going to be restarted. I am not as worried about nuclear power as many people are, including a lot of my colleagues. So if it was a choice between coal-fired power plants and nuclear, or natural gas versus nuclear, I would choose nuclear. But there's no reason that we have to choose that. Wind and solar are so much better an option, have so many fewer complications, that I think there's no reason to choose nuclear over them. And it takes a long time to build a new nuclear plant and have it be operational. We could get solar, especially photovoltaic, working, generating electricity a lot faster.
Thank you, David. Thank you all for your questions. I'll hand things off to Bill Wells, who will conclude our session for today.
Well, David, thank you so much for your presentation. It's stunning to me how much scientific detail is already understood and probably on average very poorly presented to the populace. But what you've presented has given us I learned a couple of new things today. Number one, tipping elements. I had not heard that term before. And they're associated with tipping points, and I understand that better now. And I understand that some of these tipping points are imminent in the near future, and others are long-term. So I guess that presents some hope that we have a chance.
Yeah.
So thank you once again.
My pleasure. Thanks for the invitation.
Thank you, everyone. Have a great day. We'll hope to see you soon. Enjoy the warm weather today.